Um, so I'm going to do a little bit of setup, and then hopefully we'll be able to sort of work side by side in doing this bounding exercise. I'll confess that I originally wrote the code for this in R, and so I think that the code that I wrote in Stata is like my sort of bastardized attempt of making Stata work like R. So there may be some things that are like not as elegant as they could be, but I was still teaching myself how to do this yesterday, so that's where we are. That's right. Particularly with graphing, R has such beautiful things for like 3D graphing and stuff. That's all very satisfying. So, okay. So here we are. We spent the morning talking about setting up our principal stratification problems. I hope you found the exercises to be really useful in practicing some of this, articulating what do we mean by a strata and how we define them, and how you might struggle with different assumptions that ultimately are helpful in making estimation a little bit easier. So in the principal stratification problem, hang on. This is the one that's not going to be on the website, but it should have been emailed. Was it emailed? It should be like number 2. On the email there were multiple PowerPoints. Yeah. So this is like PowerPoint 2. Oh, part 2 was not emailed? It was printed, so there are at least hard copies. Yeah. That might actually work out well, because if you have the do file, then you can have the do file in your whole screen, and having this in hard copy on the side might not be a bad strategy. But yeah, there are hard copies in the back. Sorry about that. So the reason for that is that the reason I don't want it to be online is because we are using an example from small schools of choice. I can't even guarantee that the marginal values are exactly right, and they're sort of a preliminary estimate of things that we're going to play with, and so they're fairly protective of sort of the reputation and branding and results associated with small schools of choice. So it's going to be better for everybody involved if that doesn't live freely available online. I don't want to cross Howard Bloom. That would be bad for your karma, I think. He what? I feel like it would be bad for your soul to do that somehow. Okay, so getting back to the idea of what's the fundamental problem when we think about estimation, the fundamental problem is that we sort of wish that we knew we've defined these potentially substantively meaningful groups, and if we could actually observe cleanly membership in all of these groups, then estimation would be quite easy. But because these groups that we've defined as substantively meaningful are not actually directly observable, we have a little bit of a conundrum. So if we knew the Stratum membership, we would have a randomized experiment with classic subgroup analysis. We don't, but as we saw, we can still use this framework to motivate the setup of our problem. And one of the key points, as we talked about a little bit this morning, and I'll provide you a simplified example to hopefully bring the point home, is that some of our observable outcomes, what I'm going to call sort of the marginal values on our principal stratification boxes, those observable values, if we're thinking about means, those are means of distributions that are mixtures, right? In those distributions, there are different types of people, okay? So here's a very simple example. So back into the world of non-compliance, let's think about one-sided non-compliance. So in a case of one-sided non-compliance, under assignment to treatment, you can have people who are going to take up. They're going to be our compliers. People who don't take up, those are never takers. There's no opportunity for folks assigned to the control group to cross over. So there are basically no always takers and no defiers. Okay, so we're in a setup of one-sided noncompliance. Okay, so suppose we have a continuous outcome, such as a standardized test scores. So we want to ask the question, well, what are the outcome distributions that we would observe for those assigned to treatment and those assigned to control? Because of the structure of the problem, we're able to observe stratum membership for those who are assigned to treatment, right? So because there's no opportunity for crossover, it's one-sided noncompliance. For those who are assigned to treatment, we know what group they belong to because it's directly observable, right? If they take it up, they're compliers, and if they don't take it up, they're never takers. But what we don't know is our distribution here for those who are assigned to the control condition is going to be a mixture, right? That single distribution is going to include our compliers and our never takers. So just to give pictures to those words, if we looked at the distribution of outcomes, so now we're thinking about distributions of outcomes, so the observed Ys, the observed outcomes. If we thought about the distributions of outcomes for those who are assigned to the treatment condition, we can separate these groups out. And so under treatment, we could actually plot, if we had our data, we could look at a histogram of values for the students we identify as never takers and the students we identify as compliers. Does that make sense? Yeah? So this is for those who are assigned to treatment, right? But for those who are assigned to control, this is what we observe. We just have a single distribution, right? And this distribution is a mixture of the control outcome for our compliers and the control outcome for our never takers, right? And ideally what we'd like to be able to do is pull apart those two distributions, right? So in reality it looks like that. We have two different distributions, but all we're able to see is that. Okay? Okay. Okay, so there's sort of good news, bad news. The bad news, we talked about this at least in a sort of side conversation, dealing with mixtures is hard. If you actually want to disentangle and characterize those distributions, there are ways to do it. And the ways that we've done it in the past is with sort of big Bayesian models where you have lots of assumptions embedded in those models, and it actually gives you a sort of algorithmic mechanism for pulling things apart. But in doing that, lots of things that can go wrong. So Luke and Avi, who's not here, have written a paper where they begin to understand or begin to explore the many, many, many different ways that you can go wrong in that sort of algorithmic estimation process. It's not impossible, but lots of challenges can arise. And so we're not going to go in that direction today, although if you're interested in that direction, we can certainly point you in the direction of lots of papers. That's what we did in the Head Start example that we talked about this morning. That's the approach that we took and we present in the paper. But instead, what we're going to do is focus on sort of more fundamentally figuring out, well, what can we learn and what can we point identify, and when we can't point identify, what can we place some bounds around? Okay. The good news is that we can estimate things like mixing proportions. So we can estimate the share of students in our sample in this simple one-sided compliance example. We can estimate the share of kids who are compliers, and we can estimate the share of kids who are never takers. So now we're getting into the space of the fact that there are lots of things that we can know about our strata, even though we can't know exactly who belongs in those strata all the time. We can learn oftentimes what covariates are associated with which strata. Even when we can't pull apart our mixtures, we can bound certain treatment effects. And so that's where we're going to be turning today. Okay, this is just a repeat of a point that was made on the previous slide. So with certain principal stratification specifications, and this is where those assumptions become very, very important. So like the monotonicity assumption, the assumption that we called irrelevant alternatives in the Head Start example, where basically you wouldn't expect the Head Start offer to move people from center-based care to home-based care, for example. The assumptions that allow you to X out some of the cells become really, really important and fundamental to be able to move yourself forward a little bit in this process. In general, we want to be able to like X out as many boxes as possible. Also, in general, if you have, say you have a principal stratification setup in its most general that's defined by like R by C number of boxes, like number of rows, number of columns, you can learn a lot about your strata and certain stratum-specific quantities, such as the distribution of individuals and average baseline characteristics in each strata, if you're able to X out R minus 1 times C minus 1 boxes. So for example, if you have a 3 by 3, you need to be able to X out 4 boxes, and at least one cell remains in each row and each column. Right? So if you have that kind of setup, then you're going to be able to rely on marginal values of your strata in your principal stratification setup to learn a lot and estimate a lot about each of the groups in the setup. Okay? So this is sort of a general rule, and we'll investigate how this actually comes to fruition as we move forward. Okay? Okay. I'm going to go very quickly through the next few slides, and it's something that sort of we talked about from the group that presented on small schools of choice in our prior session. But what we're basically going to do is continue on with thinking about that on-track status as our sort of key intermediate behavior, and thinking about high school graduation as our outcome. So just to remind everybody, the data or the application that we're focusing on comes from New York City, comes from the opening of all of these small schools of choice in the early 2000s, together with the high school selection process, the very complicated high school selection process that was implemented in New York City, or revamped in New York City. I don't know how long that kind of school choice existed in New York City, for kids to filter into different schools. And what they basically determined was that this school choice process led to many, many, many different, I think it's on the next slide, naturally occurring lotteries. So kids had to rank schools, and then based on their rank order, they're essentially randomized into different schools, sort of conditional on those rank orders. And Howard Bloom, who you have heard a lot from in the past couple days, together with Becky Unterman, who's at MDRC and a doctoral student at Harvard, they've done a lot of work to investigate the impacts of the small schools of choice. Okay? So findings from their work, and when I say our team's work, I mean Howard and Becky. So they found that the small schools of choice increased the proportion of students who are on track. At least for now, we're going to make the assumption that on track, that the definition of on track is stable across SSC and non-SSC settings. So it had a big impact on track status. It also had a big impact on timely high school graduation, so graduation within 4 years. The SSCs cost less per graduate than their control group counterparts, and they also increased post-secondary enrollment. So there's a lot of sort of excitement around the SSCs, or they've generated a lot of positive impacts. And there's Howard and Becky are continuing to do a lot of work to really unpack why this is. What is it about the small schools of choice? One thing that Becky really underscored, if we think about this on-track status variable, one thing that she often underscores in our conversations is that policy-wise, she would argue that this is actually a really important sort of indicator to be thinking about. You know, the way that she would frame it, and there are problems with this, but the way that she would frame it is sort of a question of, well, what if it's the case that there's this sort of inoculation effect to a positive 9th grade experience, and maybe that's all kids need to then help get them on the right trajectory through high school. And so, you know, if it's the case that ninth grade on track, that you can really move the needle for kids in ninth grade, perhaps that's really the magic bullet. Now the problem, of course, is that the kids for whom the needle was moved in ninth grade still continued to get other things downstream in the SSCs. But that kind of thinking is motivating our question around whether the graduation outcomes that we see are realized most for the students who were moved to be on track as a result of the opportunity to participate in an SSC. Okay, so there's our research question. So does the impact of SSCs on four-year high school graduation potentially stem from their impact on getting students to be on track at the end of ninth grade? Okay, so here's the general principal stratification setup that we're going to look at. So under assignment to treatment, students could either be off track or on track. And then if they're assigned to control, they could also either be off track or on track. So just as the group had defined back there, we have students who are never on track. So I'll denote them as NOT, students who are induced on track, IOT, and students who are always on track, AOT. And then we have students who are induced to be off track. As we discussed this morning, maybe this assumption is, we should be careful with this assumption. Here, I'm going to apply the monotonicity assumption and assume that group away, but that could use more reflection, perhaps. Okay. Any questions so far? We're good? Okay. Okay. So just a little bit of notation, because we're going to move into the space of really thinking about the relationship between some of the values on the margins of this table and some of the values in our strata in our setup here. Okay, so just a little bit of notation. Z indicates treatment assignment. We've seen that already. T indicates whether somebody is off track, T equals 0, or on track, T equals 1. So P sub ZT indicates the share of students assigned to treatment condition Z who have ninth grade on track status T. And S indicates strata membership in the strata NOT, IOT, or AOT. And pi sub S is going to indicate the share of students in stratum S. Okay? So we'll use this notation a lot as we go through. Okay, so what I've done here is I've just labeled the terms that I've defined. So P sub 1, 0 are students who are the 1 assigned to treatment assignment, but 0 are off track. P sub 1, 1, those who are assigned to treatment and on track. Similarly, here, P0, 0, those assigned to control and are off track, and similarly for P0, 1. And then these values are the share of students in each of the strata. Okay? So it's useful to be very clear about the relationships among these different marginal values. So just to be really, really crystal clear, the sum of these two proportions, those are going to sum to 1. Across the top, the sum of those two proportions also sum to 1 on the margins, right? So the marginal proportions sum to 1. And then in our strata, the proportions within the strata also sum to 1. Okay? Easy enough, right? Okay. So now, so there we thought about the relationships on the margins and the relationships of the strata. We can also think about the relationships between the strata and the margins. Okay, so that's what we're going to do next. So here we can see that because we made this no defiers assumption, because we made this monotonicity assumption, and this is the machinery of IV as well, right? At least some of it. Because we made that assumption, we can learn something about pi NOT from the marginal value, right? So pi NOT, the share of students who are never on track, is going to be equal to this marginal proportion. Okay? Here, P11 is going to equal the sum of the pi OT and the pi AOT. Okay, and similarly, we can go down the columns. So P00 is the sum of these two, pi NOT and pi IOT. And here, P01 is just equal to pi AOT. Right? So what that lets us do is write expressions for the values of the share of students in each of these strata based just on the marginal information. Okay? And so what's nice is that in the, it's not on the board anymore, but in the Head Start example, even though you started out with a 3 by 3 table, so you have 3 by 3, as long as you block out 4 cells, there's at least one cell still alive in every row and every column, you can go through the same process here to estimate the share of students in every one of those cells. Right? So you can go through this same kind of exercise even with a much more complex setup as long as you've assumed away enough cells. So if you have R by C, you have to eliminate R minus 1 by C minus 1. And you have to have one cell alive in each row and column. So for example, if you have, I think that's right. Yeah, that should be right. Yeah, that's right. Okay, okay. Okay so far? Okay so far. Okay. So in the data, these marginal values are all observable. Okay? So this is where we're going to sort of toggle back and forth between Stata and, so you don't fall asleep. You have something to do with your hands besides your email. So if you have the do file that I put together, oh, that's bad. Okay, here we go. Oh God, what did I do? Hold on, let me just close that and reopen it. So if you can open this Stata file. Oh, it's still over there. Oh, I know.
The one that says balance calculation?
Yeah. I like dragged this thing over here and now I can't get it back. Well, let's look at this for a second while I figure that out. Okay. Where did it go? There we go. Does everybody have this data file? Yeah. Let's see what happens if I open this one. There we go. Okay. Okay. So I'll just leave it there for now. So in the do file, can everybody see it okay from here? Okay. So the first thing that I did in the do file, so this isn't written like reading in a data set and analyzing the data. It's more in sort of matrix language, not meta in Stata, but just sort of matrix notation and working with matrices in Stata. So the first thing that I do is I just establish the values of those marginal proportions. And these marginal proportions are marginal proportions that we would estimate in the data, right? So we've used the student level data to estimate these proportions. And now we're basically just going to do as much as we can with the values that are on the margins of those of our principal stratification setup. Okay. So what I've done is defined the values, the estimated values for those marginal proportions, and then just express the formula to calculate or estimate the values for the proportions in each of the principal strata, right? So I have my formula here, and then I can just ask Stata, I can say display those values that I've calculated, and Stata will give them to me. Right, so we could just run that a little bit. And there are our values. So we estimate in our data over here, 35% of students are never on track. 14% of students are induced to be on track. And 51% of students are always on track. Okay, yeah? Exactly. So that 14% should be exactly the same as if you just regressed on-track status on your treatment indicator. And to estimate the treatment effect on on-track status, we would get 14%. At least we hope, right? So remember this morning when we were talking about the idea that that treatment effect on our intermediate behavior is sort of embedded in everything else in our table. That's where it's showing up. Yep. Any other questions? Okay. Okay, so if we go back here, I wonder if I can still, yes, I can. Okay, so far we've estimated all of these proportions. Okay, so the next thing that we can do, and this is something that I like in particular for very, very clear thinking. So the way that I've denoted basically the observed outcomes is with these thetas, right? So theta 1, 0 is the outcome for students who are off track and assigned to the treatment condition, right? So these are sort of the marginal values of the outcome, or what we actually observe for our outcomes. Theta 1, 1 is our outcome. So did they graduate or not? Did they graduate on time? So we're still working in a binary outcome. Did they graduate or not under assignment to the treatment condition if they were on track? Similarly over here. And then in each of the 4 strata, we need to think about what's the value of that outcome for students in the strata given they were assigned to treatment, and students in the strata given that they were assigned to control. Okay? So in terms of the outcome, in each strata, we have 2 values that we actually want to estimate. Right? And the difference between those 2 values, or the difference between those 2 means or proportions here, is going to be the ITT effect specific to that cell. Okay? Okay. Some of these stratum-specific values, again because of this no defiers assumption, some of these stratum-specific values can be point estimated. Right? So there are 2 here, 2 here, 2 here. There are 6 values in total that we want to be able to inform. We're able to sort of point identify for the never on track students the average of the outcome or the proportion under assignment to the treatment condition, right? So that's just going to be equal to this marginal value. And similarly over here, we can identify this value. So for those who are always on track, this value is going to be equal to the marginal value up here. And so we can point identify that as well. Now suppose, so here's a question. Suppose we also wanted to, and we're not going to, but suppose we also wanted to apply exclusion restrictions. So if we applied exclusion restrictions, what else would we be able to say something about? Can you see the slides okay? So what are our exclusion restrictions telling us? So there are different kinds of exclusion restrictions. So let me be more specific. what if we wanted to say, you know, for these kids who are always on track, whether they're in an SSC or not, it's going to have no bearing. We're going to feel okay saying 0 treatment effect here. What would that tell us about the value of this parameter? What would we set it equal to? Not 0. Theta 0, 1. Because we want the difference, if we're assuming an exclusion restriction, we would say the difference between theta 1 AOT and theta 0 AOT is equal to 0. Right? So another way of saying that is that theta 1 AOT is the same as the marginal value of theta here. Right? 0 treatment effect. And what about over here? So if we said the never on track students, we're going to assume an exclusion restriction, what would that buy us in terms of informing theta 0 NOT? That's right, that it's equal to this value, right? So that's a very sort of concrete example. If we assume that exclusion restriction, here it allows us to inform the value of this specifically. And if we assume the exclusion restriction down here, it allows us to inform the value of this specifically. Okay? We're not going to apply an exclusion restriction here, but I want you to see how it would be operationalized. And that's how we would operationalize it here. Low energy. Everybody needs a coffee. Everybody was so, I don't know. Teaching in the afternoon is terrible. Okay. Yeah. So sorry about the notation. So P, it's because everything is zeros and ones. So the P's are the proportion of students in each marginal box. Observed. P's, the P's are observed. So everything on the margin, those are all observed. Those are things we can actually observe in our data, right? So here, let's just focus on this cell for a second. P01 is the share of students who were assigned to treatment. Let me say it a different way. Of those students who were assigned to treatment, the share who are off track. And of those students who were assigned to treatment, the share who are on track, such that P10 and P11 sum to 1, sum to 100%. And similarly across the margin, across the top margin here, for P00 and P01. So the P's are telling us the proportion of students along those margins conditional on treatment assignment. We'll stick on the margins for a second. The thetas are the outcome, basically. You can think of those as the outcome. So here, it's did you graduate or not? So you can think of the thetas as a proportion as well, right? So here, the share of students on this margin who graduated on time. Here, the share of students, conditional assignment to treatment and being on track, the share of students who graduated on time. And similarly up here. Does that help? And then the pies, so far the pies are the share of students in each of the strata. And then these are the stratum-specific value of the outcome under assignment to treatment and the stratum-specific value under assignment to control. So these stratum-specific thetas are what we want to inform with the bounding that we're going to do. Well, so they're all parameters of interest, right? I think they're all parameters of interest. So once I, hang on, I have hats on them. I think I tried to put hats on everything where they're actually estimated. But otherwise, we could think of everything as being a parameter. Yeah. And in terms of uncertainty, eventually we'll put a bootstrap on top of this and just do it over and over and over again. Okay. Okay so far? More Stata. Okay. Let's see. Okay. So we talked about what would be happening with the exclusion restriction. We're not going to induce an exclusion restriction. So we basically have four quantities. This outcome under control condition, these two outcomes under both treatment and control, and over here. So we have four different quantities of interest that we need to put bounds around. Okay? So what we're going to do is investigate. What we really want to think about is, like, how much can we learn from the value on the margin, and understanding that because we have this marginal value, that marginal value is going to inform what these two values can be, and it's going to inform a trade-off that we're going to experience between those two values, right? So because we know this theta 1, 1, this theta 1 IOT and this theta 1 AOT are component parts of this theta 1, 1. So we're going to use this theta 1, 1 and the relative size of these two cells to understand what are sort of plausible values. And when I say plausible, I mean what values could actually occur in the data given this marginal value. Okay, so let me show you in math what I mean, and we're going to, on the next slide, I get rid of the rest of what's on this, and I just focus on this row. Okay, so I just want to be clear about that. Okay, so I've just taken that same row and I've moved it up to the top. Okay, so what I was trying to wave my hands about and say in words is that theta 1, 1, this marginal value that we observe, is just a weighted average of theta 1 IOT and theta 1 AOT. And the weights for that average are just the relative size of these cells, right? So the weight here is going to be theta IOT over the sum of, I'm sorry, not theta, pi IOT over the sum of pi IOT plus pi AOT. And then over here, the weight is just the opposite of that. So pi AOT over the sum of the two pi's. Okay? So for the sake of notation, because all you want is more notation, we're gonna set this weight. I should have used omega or something, but we're gonna set this weight equal to phi. Okay, so this weight is going to be equal to phi 1, and over here 1 minus phi 1. Okay, is everybody with me? So big idea is that the marginal value is equal to a weighted sum of the stratum-specific values. Okay, here's where it gets cool. Okay, so that's what we saw in these first two. And now in this expression, I'm just taking this, and I've replaced these fractions with phi 1 here and 1 minus phi 1 here. Okay? So what we have is we have one equation and two unknowns. Okay? So that's what we've boiled it down to, one equation and two unknowns. Okay? So there's our one equation and two unknowns. And what we're going to do is we're just going to rewrite it. Okay? We're going to rewrite it so I'm just sort of algebraically moving business around. I'm going to rewrite it so that we can express theta 1 IOT, the value of the outcome, or the outcome proportion in the IOT cell, as a function, as a linear function of theta 1 AOT. Right? So what this expression is telling us is that there's a trade-off between the value of that outcome under one cell and what that value can be in the other cell. Right? And we have that trade-off because the margins of our table are fixed. Okay. Okay, is everybody with me? That was not convincing. Yes? Okay? Okay. Okay, so now I've put the hats back on. Now I'm showing you these marginal values. So what do we see? Under assignment to the treatment condition, for students who remain off track under treatment, 38% of those kids graduate on time. Under assignment to the treatment condition, for those who are on track, 89% of those kids graduate on time. And similarly over here, for those who are assigned to control and they're off track, 34% of kids graduate on time. And here, for those who are on track, 86% graduate on time. Okay? So in my Stata code, the next thing that I do is I just set the values of those marginal values. Okay? And then the other thing that I do is, remember how we had that phi expression? So phi 1 was the ratio of induced on track over induced on track plus always on track, the pi's. So I just set the values for the phi 1 scalar and the analogous, I called it phi 0, when we want to calculate bounds for the control values. Okay? So that's all I've done here. Okay. So far, so good? Okay. Okay. So we're going to return to thinking about this expression right here. So this is the expression that gives us the trade-off between the value of the outcome, this proportion, under treatment for those who are induced on track, and the value here under treatment for those who are always on track. Okay? Our outcome is high school graduation. It's binary. So that means that these are proportions. They can take on the values between 0 and 1. And knowing that is quite convenient, right? So pi 1 AOT can only be between 0 and 1 at its most extreme. Okay, so we're going to start out with that idea with values between 0 and all the way up to 1 for pi AOT, and basically plug them into this expression and see what we get for pi 1 IOT. Okay? So this is where it gets exciting. It's already been exciting. Okay. So we can do that. So what have I done here? Here, I'm just, you can see that I say matrix theta 1 AOT. And this is just notation for saying, give me 101 observations, or give me 101 rows and 1 column, and just make it blank for right now. So I'm gonna populate what's in that matrix, and that's what I'm doing in here. With this loop, I'm just populating that. It's like a column vector. I'm just populating that column vector by saying let it equal 0 and then 0.01 and 0.02. So I'm just counting up in increments of 0.01 from 0 to 1. Okay? I'm doing the same thing. Oh, and then what I'm doing here is I'm calculating the values for theta 1 IOT conditional on those values that I've set for theta 1 AOT. Right? So it's saying, well, if theta 1 AOT is equal to 1, then theta 1 IOT has to equal this, right? Because there's a perfect trade-off between them. Okay? So if you run that bit, here you can say matrix. How much like matrix kind of business like this do you guys do? Some, like you've seen these kinds of stuff before? Ish, okay. So here it's always good to just like check if your thing's populated the way you think they're going to. And then this is the one thing where Stata is a little clunky for this. So in order to calculate anything with these values that you generate, to do any plots or do any means, you have to take the matrix objects and translate them to data in Stata. And that's what this SVMat, I learned this yesterday. That's what this does. Okay. And so now I'm here creating basically variables in a data set that will allow me to do some manipulation. Okay. I know that I hope that this is okay. Yes, it will freak out. So you don't want to have a loaded data set.
And then after those two lines, you have a synthetic data set that has two variables, theta 1 AOT and theta 1 IOT, 101 observations.
That's right. That's right.
Are basically pairs of possible treatment effects.
Exactly. Not treatment effects.
Sorry, pairs of possible means of the
Outcome. Yep. Yep. So we can do that. And then what I think is really nice is then you can create a scatter plot. So if you just run through here, and I do that, hopefully something happens. What happened? Phi1 not found. I didn't run enough. There we go. There we go. Ah. Okay. And so you can get this plot. And this plot is going to tell you about the trade-off in the possible values between theta 1 IOT and theta 1 AOT. So what do you see when you look at this plot? Besides a straight line. What do you observe when you look at this plot? The theta on the y-axis goes above 1. Yeah. Yeah, right. So if we just said, let's let theta AOT run between 0 and 1, if theta AOT were all the way down here, the graduation rate for theta IOT would have to be impossible, right? It's not possible. So we've generated these values with no attention to what's possible in the world. And so now we can restrict this according to what's actually possible in the world. Okay? So if we go back to our Stata code, what I did was I just to provide a visual on it, I said, okay, give me my original scatter plot, because I wanted to see them all together. Give me my original scatter plot, and then overlay the same scatter plot, but only if the values that I've calculated for theta 1 IOT are between 0 and 1, and theta AOT are between 0 and 1. And give it a different color so I can see how much I've lopped off. So if I do that, then what I see is that even though I started off with all of these values over here, everything that's in blue is not possible, right? Because the theta 1 IOT is too large, and so the vertical here tells me about the range of theta 1 IOT that's possible, and the horizontal range tells me about, with no other restrictions, the range of theta 1 AOT that's possible. And that's exciting. And then we can just calculate some summary statistics. And so we can see that based on these calculations, theta 1 IOT can range between about 0.49 and 100%. So still pretty wide, not perfect. And we see for theta 1 AOT, it's really quite narrow, right? 86% to 100%. Okay. Okay. So what have we learned? So far what we've learned is we've estimated bounds for this theta 1 AOT. Here, 86% to 100%. And here, this theta 1 IOT, 0.49 to 1. Okay. Yeah? Right. So that's why I picked a binary outcome.
So is the principal stratification only useful when you're
Well, but you could at least say in your data, like if you have a continuous distribution, you could at least say there's this continuous distribution, and I'm going to lop that sort of observed data up into this group and that group. And so you could at least say, okay, if 15% of that distribution is made up of this group, you could say, what if that 15% is the highest 15%? And what if that 15% is the lowest 15% in the data that I observe? Right? And That's basically what's happening here. It just, the calculation of it is so nice because it's zeros and ones. But you can basically do the same thing if you have a continuous outcome.
Are there any cases maybe where you might have a sense, a priori of what that value, like what theta AOT might be for some other study?
Right. So there you're getting into the idea of like, can we bring in sort of a little science and knowledge and understanding to, and we'll do that, right? We'll do that, and once we bound a few more things to say, well, what if we wanted to say plausibly that, gosh, the treatment effect for those who are induced to be on track, it must be larger than the treatment effect for those who are never on track, right? Or as you're saying, it must be the case that the value of this outcome has to be larger than the value of this outcome, right? We would just believe that that's true, right? So we could look and see. I didn't calculate this, but you could go to Stata and say, tell me. It's always bad to do things on the fly. Okay, we could say, Stata, tell me, give me summary statistics for these two guys if theta 1 IoT, IoT is less than theta 1 AOT. What do we get? And we can look and see. And so if we do that, then we tighten our bounds even further. We say, oh, wow, look, theta 1 AOT has to be between 90 and 100%. And theta 1 IoT is between 49. Our lower bound is the same, but our upper bound is a little bit smaller. We've narrowed further, right? So what's nice about this kind of exercise, I think, is you can have all of these sort of plausible assumptions or sort of plausible ideas of what's going on in the trade-offs between these two cells, and you can apply those sort of plausible sort of understanding of the way the world works to see if I apply those things, by how much do I tighten these bounds. Yeah?
Cynical. So, like, whenever I've tried to do bounds and stuff, everything's just huge unless it's just really narrow imbalance and sort of trying to observe differences. So, like, it's hard for me to imagine a context in which, like, 49 and 85 is pretty big.
Yep.
But, like, in your own work, do you do this and find examples where the sort of bounding is such that it's actually feels like really useful to you?
So I think the example that Luke's going to transition to in the early college high school application is one where even these first order bounds provide substantively interesting information. So for example, and I think this is one too in cases. So if we go back to the slides, like what have we learned here? So we've learned that, or we've estimated under assignment to the control condition, 86% graduation rate, right? And under the treatment condition, it's 86 to 100%, right? So we made the no defiers assumption. We relied on that. We didn't make any other assumptions, I don't think. And here we can say, okay, well, for this cell, we can confirm that for maybe relatively high-achieving students, the SSCs don't seem to have a detrimental impact, right? So that's something. It's not everything that we're looking for, but that's something that we see here. So there's a range on our treatment effect that's 0 to something pretty positive. Are you convinced? Okay. So then we can do the same thing for the control group. And I was going to say to take a few minutes to sort of try it yourself, basically to calculate bounds for these two values. Do you want to try it yourself, or do you want me to just put up the code? Well, so the code actually is down at the bottom of the do file. I just dumped it down there so that it wasn't right up there. So why don't you take like 5 or 10 minutes to like test your understanding and see if you can come up with bounded values for these two. Is that okay? Okay. And if you just want the answer, it's at the bottom of the do file. about now? Is that good? Okay, so how'd we do? Okay-ish, yeah? Some thumbs up, some thumbs up? Okay, so the scatter plot that I get looks like this for theta 0 NOT and theta 0 IOT. So what's happening with the outcome for these folks under assignment to control, for those induced on track, and those who are never on track. So compared to the other slide that we looked at, what do you see, or graph that we look at, what do you see when you look at this? Right, neither goes above or below 0 or 1, and so we don't get that satisfying feeling of restricting this. So we see that there's still quite a lot of range here. So we see that theta IOT can still plausibly be between 0 and 100%. Theta 0 NOT can basically be between almost 0 and about 49%. Okay. So we can fill that in here. And so here are the values that we filled in. So here's the theta 0 NOT. It goes from about 8% to 48%. And theta 0 IOT still goes from 0 to 100%. Okay. So first order, we see, and this is probably, Ojed, your more typical experience when we try to estimate these principal causal effects in these different cells, we see that they're still quite large, right? So in the never on track cell, we see that without additional assumptions or information, this could be between negative 10% and positive 30%. That's a lot of range. And here for the induced on track, arguably the group that we care most about, it's negative 0.51 all the way to 1. Okay. So then we might want to, there are a bunch of different things that we can do to begin to tighten these bounds. And I want to hit on two kind of a little bit briefly, because I think there's a lot that you can do to play around. And then we'll take a break, and then when we come back, I still have a few things to say. There's one other thing I want to show you, actually. Luke is going to show you how to incorporate covariate information to tighten bounds further. Okay? But here's what I want to still do. Let's look and see. Okay, so one thing that we might do is sort of begin to make assumptions, either about the stratum-specific theta 1 and theta 0 values, or we might start to make assumptions about the principal causal effects, right? To say, well, maybe it's the case that the effect on graduation in, say, the induced on track cell, we're going to reason that that has to be larger, for example, than the treatment effect in the never on track cell, right? So one thing that we could do, again, is to begin to make assumptions about which of the trade-offs that we calculate are really reasonable, okay? So just one assumption that I want to offer, and I think this relates to an assumption that you guys made in your group, so I'm glad to see that. We might say, okay, in this induced on track cell, let me go up just one. In this induced on track cell, since these were the students who were really moved to be on track, then maybe it would be reasonable to argue that in this cell, the treatment effect really can't be negative, right? That the treatment effect in this cell would be 0 to positive, right? And so if the treatment effect in this cell were 0 to positive, then we could say, okay, theta 0 IOT can't go all the way up to 1. It can only go to 0.49, right? So we could lop off the possibility of theta 0 IOT being greater than 0.49, okay? And so if we did that, graphically, and that's what I do here, then this is the thing that you were running before. Graphically, if we do that, we're going to just keep the observations in red, and that assumption allows us to lop off all of these possibilities, right? So it's narrowing bounds both in the induced on track cell as well as the never on track cell. Sean?
So, in that cell, that induced on track cell,
Yep. I think that's the general idea, although maybe I have that wrong. And when we transition to thinking about these trade-offs with principal causal effects instead, then maybe that suggests that thinking about those kinds of restrictions would be better once we're dealing with principal causal effects rather than with the sort of component parts of them. So it's a good question.
Yeah, I mean, we may not care about the thetas actually, we just care about the principal causal effects. So
Right.
but it wasn't obvious to me that constraining the effect to be positive constrains
The component parts to be positive.
parts
Yeah, yeah, yeah.
for having a control upper bound that's no higher than
Right. Right. It's a good point. I mean, I think typically, so I think the thing that motivated me is that typically in estimating these kinds of bounds, you sort of go through this exercise of saying, well, like, how bad could it be over here and how good could it be over here? And using those best and worst case scenarios to calculate your bounds. So that was what motivated me. But your question is making me think that we might be better off exploring this question more in the space of the principal causal effects rather than the component parts. Okay, so TBD on that one. So with that in mind, the last thing that I just wanted to walk through very quickly is thinking about the interrelationship between the different principal causal effects, right? So we saw that there's an interrelationship between the values of the theta 1s in the different strata and the theta 0s in the different strata. And given those different interrelationships, sorry about these, given those different interrelationships, we can actually express all of the treatment effects. So here's the treatment effect for those who are induced on track. That treatment effect is just going to be the difference between the theta 1 IOT and the theta 0 IOT. We can express the principal causal effect for the never on track and the principal causal effect for the always on track groups also in terms of here the theta 0 IOT and here the theta 1 IOT. So I haven't done the whole derivation of these interrelationships, but you could go ahead and derive those from the equalities that we've looked at already. Okay, so then the last thing that I did was I wanted to sort of plot and understand the relationships between the different principal causal effects. So what I did in order to do that was I basically just started off with like building, you could think about it as like a grid, right? So if we have a grid for possible values of theta 1 IOT and theta 0 IOT, so we could say, you know, it's possible that theta 1 IOT is equal to 0.75 and theta 0 IOT is equal to 0.6. So that treatment effect is 0.15. And once we calculate those two values, it's going to, those values, once they're fixed, are going to inform what the principal causal effects have to be in the other cells, right? So I create a grid of the theta 1 IOT, the theta 0 IOT, and for each combination of those theta 1 and theta 0 IOTs, you can calculate the principal causal effect for the IOT cell and then also for the other two cells. Does that make sense? I know I'm kind of waving my hands here. Okay. So that's what I've done here. I confess, Sean, in response to the conversation that we just had, this is based on that, on constraining those treatment effects that we just talked about. But the machinery of it should be the same. So here what I've done is I just create, again, matrices to capture my calculated values of the three different types of principal causal effects. And then this syntax is just going through and calculating what all of those different principal causal effects are based on the interrelationships that we expressed. So I'm just gonna run this. I'm just keeping an eye on the time. And then once you want to do things with them, for each of the principal causal effects, they're actually in a 52 by 50 matrix. So the one thing that you have to do to begin to do any math with them is transition those matrices to single column vectors and then translate the single column vectors to data. And then we can begin to do some data calculations with them. So let me just say clear and run these. And so here what I've done is we have the 3 different kinds of principal causal effects, and we can look at the minimum and maximum values for them. So we see for the always on track group, we have that principal causal effect that runs from about 0 to 14%. For those who are induced on track, it's still 0 to 1. And for those who are never on track, it's that negative 10 to 10% that we saw before. So here's where we could also start thinking about and reasoning about the interrelationship between the principal causal effects themselves. And so here I've said, well, okay, how do these summary values change if we make the assumption, for example, that the principal causal effect for those induced on track has to be larger than the principal causal effect for those who are never on track? And if we make that assumption, then some of those possible values drop out. And what we see is that, particularly for those who are induced on track, this now has a minimum value of 8%. So we're saying the impact on graduation for those who are induced on track is somewhere between 8% and 1. So it's positive. It's decently positive to something quite large, right? And so there's more that we can do to continue to narrow down these bounds. The last thing that I want to show you is just a more complicated setup for principal stratification. One thing that we didn't talk about this morning is when we got into some of the other applications, thinking about compliance actually sort of dropped out, right? We never layered on top of the different applications that we were looking at whether or not individuals were actually taking up the treatment, right? And so we investigated, well, can we think about making this principal stratification setup more complicated by simultaneously thinking about this off-track status variable and also whether they took up the opportunity to enroll or not, right? So here, my strata are defined by both compliance and on-track status, right? So the possible values are take-up of SSC and off-track, non-take-up of SSC and off-track, take-up of SSC and on-track, not taking up the SSC and on-track, okay? And then there are 3 different types of assumptions that will apply to reduce the cells. So first, we assumed monotonicity of SSC take-up. So it's like no defiers on compliance, basically. We assumed monotonicity of on-track status, so no defiers on on-track. And then this sort of considers the cross-referencing of both of them. Okay, so here we said it's an exclusion restriction with on-track status as the outcome, right? So if a student doesn't take up the SSC offer, we assume that the offer cannot impact on-track status, right? So that third assumption is, again, this sort of cross-referencing of the 2 different types of assumptions. So here we assume, for example, if a student doesn't change in terms of SSC, they can't change in terms of off-track to on-track, right? So that rules out this cell. And over everything else, I guess this is the other one. If a student, this is the other one. If a student is always in a non-SSC, if they don't change their school type, they can't go from off-track to on-track. So it rules out those 2 cells. Those can apply here, but these cells can also be ruled out based on other assumptions. And so what's interesting is that, remember that the SSC induced on track were the ones that we sort of cared about the most. And that group remains intact from the simpler construction to this construction because all of the other sort of, so these 4 cells basically represent blowing up that induced on-track group, but we've assumed away all of the other component parts. So this group remains intact. Whereas the other ones, those who would always be off track and those who would always be on track, they're blown up into different cells. And so it's interesting, and now I'm just going to like wave my hands, and hopefully this will be a paper soon, is that in this kind of expression, the bounds, when we calculate bounds in this expression, are narrower here than they were in the previous expression. And if we actually like toggle back and forth between the 2 setups because of this equality, we can actually gain a lot of information and do a lot better with our bounds in both circumstances. Isn't that cool? So I'm so excited about that. That was one of those moments in my office where I was like, I think we've learned something. So it was very exciting for me. Okay, so that's really cool. So I hope that holds up because it's kind of new. Okay. Did any of that make any sense? Yes. I think that was my goal. Okay. So that's everything that I wanted to do with these bounds calculations. I think we'll take a break. And then when we come back, Luke is going to make it all better with showing us how to improve our bounds further with covariates and what kind of covariates we want to look for in particular.